Hi class, this is our last lab, and this has to deal with molality, which is not something that we have covered. So I've done my best to make this as easy to understand to get through this lab as possible. I will, since this is a little bit more of could be a difficult lab, if you have any questions, please email me so we can set up 10-15 minute meeting on Tuesday or Thursday to help you get through some of the parts that maybe this is a little difficult. So molality. Molality is what we are dealing with in this lab. It is different than molarity. Molality is a small m. Molarity is a big M. With molarity, it's not really discussed, but molarity can change with temperature. I'm not going to really go into that too much, but it's dependent on temperature. Experiments with molality and use a range of temperatures, and it is not affected by temperature in itself. So it's also so it's a small m, but if you look here, it's moles of solute over kilograms of solvent. Remember, a solution is a solute plus a solvent. So this is strictly a solvent at the bottom and moles of solute at the top, and this is kilograms. So moles over kilograms equals a small m. Note that molality is per kilogram of solvent and not solution. So if you were given a solution, you would actually have to subtract the mass of solute from the solvent, and that would be on the bottom. So how does molality fit into this? So we're going to be dealing with the freezing point. Freezing point depression occurs when there is a non-volatile solute dissolved in a solvent. The presence of solute decreases the temperature at which the solution freezes. Basically, what this means is that, let's say that our solvent is water and we don't want it to freeze. We're going to add something to it to prevent those water molecules from coming together and becoming ice. So it's in a way of kind of you're at a concert and you're trying to get to the stage, and yet you have the bodyguards and security blocking you. You can't get to where you want to get to. That's exactly what's happening here. It's depressing the freezing point. So if water normally freezes at 0 degrees Celsius, it now will have to have much more energy in it to get past those other non-volatile, which means not easily vaporized or evaporated away, get past those particles to come together to create a solid. So if water freezes at 0 degrees Celsius, it now, based on how much of a solute you ask, because that's that's proportional to the temperature change of it. So let's say I add a lot of salt to water, that now will make the freezing point maybe -5 degrees. The weather will have to get down to -5 degrees now before the water will freeze, and it'll stay at a liquid at 0 degrees Celsius because it's not pure. It's not pure water. We've added something to prevent that from happening. That's what a freezing point depression means. We have an equation. In this equation, I have number 2. So if you print your PDF out, and you write numbers on the bottom of it, because there was no numbers, but I always do that so I can refer to what page. This, I believe, is on the first page, but the equation is in parentheses. I got confused for a second. The equation is number 2, so I put it in here is number 2. This means change in the freezing point. So that's what I'm talking about. If it goes down maybe 5 degrees, that's what we would figure out. Kf is a freezing point depression constant. So what this means is that when we look at the solvent, which is pure, the solvent has its own constant freezing point depression. So every solution, every solvent has its own specific value. So we would need to know that we need to know what the solvent is, and we need to know what the Kf that goes with it is. And then M, that normally doesn't have solute here, but I did it to make it easy. This is the molality. So when you see M, and M is usually by itself, it's moles of solute over kilograms. You have it on your PDF as number 5, but it's rearranged weird, and this is normally the way the equation is. I don't know why they have it as so difficult on there. So here's a visual that you can see. So let's just say this is water. Water is the easiest thing to discuss. Water will eventually, through attraction of the forces, come together as a solid if enough energy is there to allow this to happen. So it will become ice. But when you add something to it, so it's kind of like making it impure or dirtying it up, you are preventing the water molecules from coming together. The attraction, the solute particles that are added to it are preventing those attraction forces to come together. It's not strong enough. So it actually has to go down lower in temperature to overcome those particles and push them out of the way to become a solid. So this is also an example of, I talked about salt on ice. This is also antifreeze. Antifreeze prevents your car from overheating, and it also prevents the fluid in your car from freezing. So it's dirtying up the solution in there to make sure that the particles do not come together as a solid, because you do not want a solid for water in your, what is it? I forgot what it is. Transmission? No, not transmission. Now I sound horrible. It's ridiculous. Sorry. I know what it is. Radiator. There it is. Radiator. I've changed it. I know. So this is just a good example of what you can see, what happens. So we are interested in B and not A. We want to prevent A. So what happens when you, in a sense, dirty up a solvent? You are changing, I said, the temperature of what it would normally do. So if water normally boils at 100 degrees, but you add something to it to prevent that from happening at 100, it will increase that temperature. So more energy will actually have to go into it to get that solution to boil, which is why you don't want your car to overheat. So it increases the boiling point, so it takes a lot more to get it to that point. Same as freezing. If water normally freezes at 0, but if we add a solute to it, a non-volatile which doesn't evaporate away easily, then it's going to push the temperature down, where it's going to have to go so much more into the negative range to get that to become a solid. So this is just more of what I'm saying here. I found a nice little picture here. Solvent molecules prevent the solute molecules from forming a solid. It has to reach a lower temperature to form. The solute will not enter the solid structure. So the solute will not allow this to become a solid, and it'll actually, when it does become a solid, it will push the impurities out of it. This is what we do in a lab, also called recrystallization, where we want a solid, and the solid will be pure and clean and away from all the impurities that were maybe stuck in it originally before the lab experiment started. This is the same thing. When this becomes a solid, it's going to push all those solute particles out of it, and it will be just that. It will not be able to become a solid with any of these particles in the way. The solute will not enter the solid structure, usually energetically favorable. This all has to do with attractions and energy in order for this to happen. Freezing point lowers to compensate for the solute molecules, preventing the solid from forming at normal. FP is freezing point. This is called the freezing point depression. Change in freezing point is proportional to the amount of solute, and that's what you can see here, which I'll go over. Salt added to icy streets to prevent water freezing. The lower temperature must be reached for the water to freeze. We don't live anywhere that has to be, but I'm sure some of you understand this and have been in cold weather. I think it's crazy. I born and raised over here. I don't know how I could deal with that. So this is a graph, and I actually do this lab at another school. Not exactly similar to, it's not exact what this lab is today. It matches more of this graph, where they start and collect the temperature of a pure solvent, and then they add a certain amount of solute, and then they graph it. And then they add more of the solute and they graph it. And as you can see, it starts changing. The temperature it starts going down from the cooling to where it hits freezing point over time. So that's what is happening, is that the more solute you add, the more particles there are to prevent the water molecules from coming together. Freezing point depression is an example of a colligative property, meaning that is only affected by the amount and not the identity of solute. So this is what the hardest thing to understand about this lab is, and even at the other school I do it at. You never know what your solute is. You do not know what the identity is. You're not meant to know, but you are going to determine the molar mass. There's enough information given that you can do enough calculations to determine everything about it except for what it is. And that's exactly, it doesn't matter what it is. We are simply using something that's non-volatile that can interfere with water molecules. In this case, we'll use a solvent as my example, and it's going to prevent something coming together. This is important because sorry, I keep saying this wrong. Solute particles simply collides with solvent particles to prevent them from sticking to each other. So there's not real strong interaction between the solute particles and solvent particles. See, and this is useful determining the molar mass. So if we can figure out what the freezing point depression is, that's the difference in what the normal would be compared to what it is. We can really figure out a lot of stuff. So this is antifreeze, melting snow on roads, or it's also lowering the freezing point, and making homemade ice cream. Colligative properties. In your quiz, there's a question about colligative properties, so I need to address it. Colligative, this lab has just got all these words. Colligative properties are properties which depend only on the number of particles in solution, not on the identity. That's what the definition is. So there's a few things that go with this. Freezing point, freezing point depression, boiling point elevation, vapor pressure lowering, osmotic pressure. This lab, we're only dealing with freezing point. We're not dealing with the others, but these are the 4 properties that go with colligative properties. Why salt to road? Colligative properties have practical applications. Applying salt to an icy road, the melting freezing point of the ice, this is an equilibrium, so it's right at the phase change of the ice is decreased, and the ice will melt more quickly, making driving safer, because you'd rather drive on water, which is rain, than ice. Sodium chloride and either calcium chloride or magnesium chloride are used frequently, either alone or in a mixture. Sodium chloride is the least expensive option, but is less effective because it only dissociates into 2 ions instead of 3, and we're going to cover that in a little bit. I'm not going to go too much into this page because, like I said, you guys didn't get to this chapter. And there's a lot more going on here, but all you need to really remember here is that there's an equilibrium of phases. So when it's talking about melting point, it's also talking about freezing point. It is in the middle of both the solid and the liquid stage. So it would be where the black line is. It's an equilibrium, so it's in between both of these phases. All right, so let's break down the equation that we're going to use in this lab. So again, I put the solute here so you can understand it, but it's really just the M. The change in freezing point is proportional to the molality of the solution. Kf is the molal, I know I'm not saying that right. I'm not saying any of these words right tonight. Freezing point depression constant of the pure solvent used in experiment. So remember I said that we need to know what the solvent is, and each solvent has its own unique Kf value to it. The molal, sounds horrible, freezing point depression constant is unique for each different solvent. So here is, this would be the freezing point depression that we need to know. It would be in Celsius. Kf, here is an example. It's not a negative. I should have just taken this part out. It's one for value of water is 1.86 Celsius over M, which is molality. And if you break this out and define what M is, it's moles over kilogram. The relationship, so here it is, it's exactly like this. The freezing point depression, and molality, which is moles over kilograms. You would have a chart of different solutions that would give you what the normal freezing point is, and then the Kf value for it. And most of the time, you're not even given the freezing point, you're given the Kf value of it. For our lab, we're using stearic acid, at least the labs that I've done on here. It's stearic acid, and the Kf value is also listed in your PDF lab experiment, but I'm giving it to you here as well. It's 4.5. So this is the Kf value. Okay, so Van 't Hoff factor is an I. It has to do with electrolytes more than anything else. So if you look here, there's an I, but when I showed you the equation earlier, the I is left out. The I is usually left out, and sometimes it's brought in. Chemistry is very interesting in this way. The I is only brought in when you're using electrolytes, because you need to account for every ion that disassociates, and that has to be factored in. But if you're using something that dissolves in, for instance, water, but stays as a molecule, then I is equal 1, and you don't need to put it in the equation. So these are those weird little things you just have to know. So pay attention to what the unknown is if it's given to you, because if it's an electrolyte, you have to factor this in. So here's an example. We have methanol here. It's 1. Why? Because this does not dissociate. It's all nonmetals, and it's going to stay as it is. 2 here, we would have an Van Hoff factor of 2. Why? Because when sodium chloride goes into water, it breaks into ions, 2 ions specifically. Here we have calcium chloride. I would be 3 because we would have 2 ions of chloride and 1 ion of calcium. And this would have 5, and hopefully you can figure it out. 3 of this, 2 of that, and that's going to give it. So you need to pay attention when you have an electrolyte. So what does this do to the freezing point of the solution? Freezing point will be lower for calcium bromide because it is an electrolyte. Why is it an electrolyte? Because you have calcium, and calcium loses its electrons to bromide. So you have one molality and 1 molality of glucose. So this it dissolves, but does not become an ion. So it stays intact. So the I would be 1, and the I here would be 3. Glucose is a molecule that does not dissociate into ions. So it's not going to prevent the water molecules coming together as much because you need more particles to block that. A larger Van Hoff for calcium bromide 3 compared to glucose. So calcium bromide dissociates into 3 ions. That's more ions, which is going to prevent the water molecules from coming together, which is exactly what I just said in the last sentence. This is just the same thing here, repeating itself. 1 mole of sugar is going to stay 1 mole, 2 mole of dissolved particles because you got 2 ions, and this one has 3. Some of these pictures are from my lab at the other school I work at. You have some questions and quizzes, and they're not that easy if you don't know what you're doing. So I have put some together of the questions that you may be asked. This looks like a lot of work, but it really is not that difficult at all. You just got to remember there's really 2 equations that you need to use in your PDF, and I've listed them. This is one of them here. Okay, so what mass in grams of sodium chloride, and giving you the molar mass, needs to be added to 1.7 kilograms of water to create a solution with a freezing point of negative 6.4 Celsius. The freezing point depression, that's our KF, of water is 1.86. This sounds like it's a lot of work. It really is not. You take your equation and you simply start pulling out what you know. So we know that the freezing point is negative 6.4. I have it highlighted because we have to do something to that. We are looking at calcium chloride, so it's electrolyte. We need a factor of 2 for the Van Hoff. KF is always given to us, and if not, you can always look that up. Not a big deal. We need to know the equation of molality, which is moles over solute. We need to determine the mass. So we don't know how much moles are in here. So we need to solve for the moles so then we can determine how much mass. One more thing to pay attention. Our solvent is water. So water has a freezing point of 0. We need to factor this in. So first thing we need to take care of here is we set up our molality. So it's X because we don't know the moles over our solvent. Next thing, we need to get rid of this negative number. Negative numbers are no good. So number 1 in your PDF is listed. It's the solvent minus the solution. So what we have is water is 0 degrees minus -6. Now we have a positive 6.4. We can go on with doing the problem. So we set up the freezing point here. We have an I factor of 2. We have our KF factor here. And then we set up the molality, and all you do is simply solve for X. This is me just breaking it down. I multiplied these together, divided them, brought them on this side, and then the Celsius cancels out. If you bring out molality, I did here, you can see now that if you solve for X, you're going to determine the moles. How did I do that? Well, I brought kilograms over, multiplied it by this. That will cancel out, leave us as moles. And I know what my molar mass is. So once I determine the moles, which is right here, I should have separated this out a little bit more. But this is the answer right here of X. But we don't want that. We're not interested in the moles. We want to know the mass that we would need to add to this. So we have the molar mass. And the mass needed... sorry, this shouldn't be here, this last part here. The mass needed for this is 171 grams of sodium chloride. I have it listed as molar mass, but it's mass, so please, I apologize for that. The moles will cancel out. It's 171 grams. Next problem. What is the molar mass? I'm talking a little fast because I'm trying to not make this as long as it might be, what is the molar mass of the unknown compound? You have 25.3 grams of unknown compound. So we don't know what our solute is in this case. To 0.200 kilograms of benzene. Benzene is a cancerous, it's not a carcinogenic solution. It's made up of carbon and hydrogen, so it's organic. And we have a KF that's been supplied to us. With the added solute, the freezing point depression is 3.12 Celsius degrees Celsius compared to pure benzene. What is the molar mass? So pretty much, it may look a little busy on here, but that's because I wanted to pull everything out. So we know that our delta TF is here. Okay, we have that. I pulled out the KF. We have that. We have our equation we're going to need. We know that our unknown is 25 grams, but we need the moles. We need moles. We are given the grams. So my X is going to solve for moles of unknown, and I'm going to put that together here. So I have 25.3 grams over X. That both of them go over my solvent. So now I am going to, excuse me, just set this up together. So I have my delta T, my KF, and my molality. And now it's just a matter of solving for X, the same thing. I bring this over. I didn't need to do factor for I, because when you don't know what the unknown compound, you just assume the I is 1. That's why you don't always see the, excuse me, the I listed in the formula. And if it is an electrolyte, they need to tell you something about it so you can figure out what the Van 't Hoff is. Same thing, I'm just going to now work this out. The C's cancel out. I extend this out to moles over kilogram because it makes it easier to see that this cancels out when I bring it over. Excuse me. So I bring this over and I multiply it, which is what I did here. And you can see kilograms will cancel out. That'll leave me with this number. And then it'll leave me with this number here, sorry. And I still have X. So I'm going to flip these. X is going on top. That one's going to go on the bottom. And I have my molar mass, which is 208 grams per mole. I broke it down in steps because sometimes that makes it a little easier to see what needs to be done. And it's 4 steps. It's not difficult. Just foreign. It always looks difficult when something's not been seen before. Determining the freezing point. So what is the delta TF? What is the freezing point of 3.1 kilograms of water if it contains 165 grams of calcium bromide? The freezing point depression constant for water is 1.86, and then we have a molar mass. So again, pull out everything that you know. First off, we need, this is an electrolyte, so we need I. I is going to be 3. We have that. We are trying to figure out what the delta TF is. We don't know what it is. And then we have molality. We're working with water, so we know the freezing point is 0. We have 165 grams of calcium bromide. I did not show this calculation, but because I had the molar mass, I got it to moles. And then we do molality, which I have my moles here, and I've been given my kilograms of water. So I have my molality. So I'm going to plug all that in and simply now start solving for that, for delta T. So the delta T gives us the solute. But this is not complete. We need to know, we have the solute, which is the solution part here, but we need to know the solvent. So we have water is 0 degrees because it's going lower. So if water's going lower, water is not going to freeze at 1.31. That's actually higher than the 0 degrees Celsius that water freezes at. So this cannot be correct. So if you have something like water, think about that. Water freezes at 0 degrees Celsius. So how can my new temperature be 1.31? It can't be. So we need to do another step. And that step comes with solvent versus solution. So water is our solvent. It's 0 degrees minus our new solution value, and it's negative 1.31 degrees. So now with the added calcium bromide, instead of this solution, the water freezing at 0, it will have to hit negative 1.31 degrees Celsius for it to start freezing. Okay, so those are 3 questions that are some revolving on the quiz portion. So that should help you with that. Now, I'm not going to go too much into this. These pictures are from the lab that I do at another school, and it's a little bit different than what you guys this lab is talking about. Basically, you're just freezing your solvent with your solute, and you're collecting temperatures while you're making additions to the solvent. So you can see the temperature being depressed. It's going to start going down. You're going to be given data to plot on a graph. This is from your PDF, but it's going to look better than this. So this one has your temperature of your solvent. This has your temperature of your solution. But when you're doing the data report, you'll be given both of these separately. So you'll have one that gives it just for the pure solvent, and you'll have one that gives it for the solution. Okay, so when you graph, there's something that you need to pay attention to. I'm going to show you copies of my graphs on the next page. If you do not know how to graph, there's tons of YouTube videos, but if you need help, this is a very difficult lab, contact me. We can meet up on Zoom very quickly, and I can go over. I use Google Docs. I don't use Excel, but there shouldn't be that much difference. So this is what your graphs, you're going to have two graphs. This is what they should look like. You have a liquid cools, so it's going to start going down. You see the temperature, it's going down. And then the freezing point. And this is where liquid starts freezing, and then it's going to plateau, and this is where the liquid's freezing over time. So this is exactly what you need, and you need this little intersection point right here, the data points. So this is my first graph. Again, I use Google Docs. So the blue is the cooling, where it's going down, and then where they connect, where the little dot, the square is, I put that little dot there. It wasn't like that. This is now freezing, where it's plateauing. So you need two equations. You need two equations on both graphs. So one graph should have two equations, and the next graph should have two equations. So what are you trying to determine from these? X is time, and Y is temperature. You need to figure out what these are. So by looking at it, I pulled it up, and I could tell that this is 510 seconds, and the freezing temperature is 70 degrees Celsius. On this one, I put the same. I put my inner. I didn't change it on this one. It's 510 seconds and 65.3 degrees Celsius. So you can see the temperature went down because of the fact that it's got to go down more in order for the solution to freeze. All right. So I took this from your PDF. And this is how you get that flat curve line that you see here. You're going to have 3 columns, and this information is taken straight from your PDF. Your pages do not have page numbers on them. What I do in the bottom is I number them. So page 2, last paragraph, tells you how to do this. It's going to give you time and data. So you're going to collect all these data plots. You're going to list your time, and then you're going to list, what I did is I just listed the whole thing on one column, my temperatures. Then I looked to where it needed to be split, and I just copy and pasted it over into one more column. So how do you know where to split these? Well, the first column, temp readings, which difference in success. I'm sorry, when I talk too fast, I get tongue-tied. Successive readings are greater than 0.5 degrees Celsius. So anything here that is greater between the difference of them, 0.5, they stay in this column. So as you can see, these are all over 0.5 if you start looking at the math on these. 0.5 or more or greater, okay? When you get to, for instance, you can see this is 60.8, this is 60, but it's still a difference of more than 0.5. So that's where you're going to get this is actually 1. So these are all great. But now you get right here to 58 and 57.8. This is a difference of 0.2. So I leave this one because these two factor in together. But the next one between these two, I can't take it and move it to the next column. And all of these now should be less than 0.5, and they all are when you look at the difference between them. You're going to do this for both graphs. In order to have this graph go like this with the plateau, you have to do this. If you don't, then you're going to realize it's wrong. You're going to be forced to split it. So it's not that difficult. This is in your reading instructions. Do this for both graphs, 3 columns. This is the example that you were given in your PDF file. And I labeled all of mine because I wanted to show this to you. So it doesn't matter. Some of these things are labeled a little different. No big deal. This is what you should have on yours if you choose to go this far with graphing it. You should have you definitely need equations. You should have the tread lines because they can tell you where these things intersected. And you should have everything labeled so you know exactly what part you're looking at, because it's really easy to get confused with X and Y, and you definitely should have those correct. Okay, why do you need to do this? Because you need these equations. You're going to use these equations that you take from your data plot. You have to use them. All right, so now on your page 5 of your PDF, it tells you why. You're going to take it's down here, so I put in a box what you have to do. You're going to solve for X and Y, but this time you're going to calculate what the X and Y are. You're not going to just take it from a visual like I put on mine. I can see what my visual was. But when I calculated this out, my calculations of what X and Y are different than what is here. And that's why. So you're going to follow these directions. What is it saying you to do? So with the first graph, so this is their example, you're solving these, you're just solving them for against each other. So you're solving for X. So you're going to take this one and you're going to equal it to this one. Remove the Y's and then just put them right next to each other, which is what they did here. And then they just start solving for X. So when they solve for X, the time is 5:32 seconds. Now you're going to take this number for X and you're going to plug it to either equation, and it should end up with the Y, and it should be the same answer for either one. So you don't have to worry about which one you use. And that's what they did here. You can see they have 532. They plug it in with Y, and they saw, and for X's, and they solve. And the temperature is 57.7 degrees. That's your calculated X and Y that you need in order to solve this lab. Okay, so this is part A. I call it part A. It's not really. As you can see, I got a lot of things wrong. So let me explain something about lab flow. Most of you guys don't know this, except for unless you go to my student sessions. I don't have a key for any of the labs. I've had to do each lab about 20 times in order to get the answers. I guess because I'm a TA and I'm not a coordinator on here. And each time I do the lab, it resets. So I have new data every single time I do this. I can't go back and save it and fix it. When I run out of attempts, I too have to start over. So I gave up on this because honestly, I know how to do this lab. I do a lab very similar. LabFlow is very interesting with how they want things written out. And if you don't write it right, it's wrong. And it doesn't tell you that. I've learned that it has these little labels for wrong sig figs and so forth. I've never seen any of it. It's all just wrong. And most of the time when it is, it's usually a sig fig, but it's not telling you that. One lab that I'll say this briefly. One lab, I was having problems. I couldn't get the right answer. So I contacted customer service. I told them exactly what I did. I know what the actual equation is that needed to be plugged in. I told them I was using that correct equation and I was still getting the wrong answer on LabFlow. They contacted me back with the exact instructions using exactly what I told them I was doing and still getting the wrong answer. So they didn't help me. I had to get creative to get the right answer for you guys. So anyways, I gave up on this and I'm not contacting them because they obviously weren't helping me. So this is what's going to happen for part A. Do not get it confused though, so please listen. You can enter wrong information for the freezing point determination, which has all of this here. You can even take my answers and plug this in. It doesn't matter to me, okay? But I'm going to credit you for this portion. This doesn't get you out of doing it. I know how to do this lab. I had right answers. You can see on the next page I got everything right. But you can enter the wrong information on part A because I couldn't figure out how I believe some of these things are just formats that I'm not writing them right. But I had the right information in order for me to correctly answer part B. So you have to have, even if it's not listed on LabFlow, you still have to complete the graphs and calculate in order to get that information that you use is going to be used in part B, and you have to have it right. So it doesn't have to be listed on part A. I'm going to credit it, but you actually still have to do it. To get those values, you're going to have to plug them into part B. I hope that makes sense. If not, contact me. I'll explain it a little better. But again, one last time. Part A, this part, doesn't matter if you get it wrong. I'm going to credit everybody for this portion because if I can't get it right, I don't understand. But I had the right values in order, so I still had to do the work. I just didn't have to put it right on, have it correct on LabFlow. But the second part, I will be grading, so you have to have this portion right. I'm showing this to you because this is just kind of a pain. So I labeled these as numbers because they don't. The ones in bold are the ones you actually have to calculate. And X, I just didn't give you my unknown. So the values that I calculated from my graph using those equations, I'm going to use that information to plug in to solve for this. So that's what I'm saying. You can have it listed wrong on LabFlow. You still have to do the work. Okay, so let me break it down. Number 3 is masosteric acid. That is our solvent. It's just subtracting the stearic acid with the equipment. No big deal. And then I changed it to kilograms so it'll be ready for us to use. Number 6, freezing point stearic acid. That was the calculated. So that was what I did when I set up the equations from each other. And this is what I came up with from my graphs. So if you look at my graphs here, I did the first graph only. I did not do the second graph. So any of my information is from the pure solvent only. And then I did the second graph. I'm just not showing it to you on here, but you'll see my numbers for it. Okay, so solve for X. So here is me solving these against each other, and I have my X is 494 seconds. I also solved for Y by plugging this in, and it gave me a Y. So I did this twice because number 7 is asking for the solution, which I showed you the graph. I just didn't do the work. I'm only showing the first one. But that's my information that I need in order. It's asking for Y. So I gave it here, I gave it here. So Y, this is the one that you're seeing on the next page, which is 69.5. So that's asking for Y on here, 6 and 7. Now, 8, you need to do both graphs. Why do you need to do both graphs? Because you got to take Y's on both of those. The freezing point depression is the solvent, the temperature change of the solvent minus the temperature change of the solution. So both of these are taken from calculating Y on the graphs. The first graph is my pure solvent. The second graph is my solution. So you're calculating for 2 Y's. So here are my Y's. I didn't do this one. I didn't show you this one, but I'm showing you my answer. And then you subtract them. This is my freezing point depression from this. So now I'm going to jump to 11 because it's kind of backwards how they have these set up. I need 11 in order to answer 9 and 10. I can't do 9 and 10 without 11. So I'm starting at 11. Molar mass of an unknown. So again, I have the same equation. I know what my KF is. I know what my unknown mass is. It was listed. I know what my delta T is because I count from my calculations. And I know what my solvent is. So now it's just plugging everything in. X, this is very similar to the examples that I've shown you on previous slides. I solve for X. Put this all together. I'm not going to show it on here because I already showed it in the sample problems that could be on your quiz. And my unknown molar mass is 102 grams for my unknown. I still won't know what the solute is, but I know what my molar mass is. Number 10, moles of the unknown. So now I know what my molar mass is. I know what my mass is. I can just solve for my moles, which I do very easily. That should look, not difficult to do. And the last one is my molality of the unknown. So number 5 is listed in your PDF, but I rearranged it because it looks weird the way they have it. And then I have moles of solute over kilograms of solvent. I know what my moles of solute are, even though I don't know what it is. I have my kilograms of solvent, and my molality is 1.07 moles. And if we go back, you can see that that's what I have listed here. So it's got a lot of calculations. It might take a little while, especially with something that we haven't covered. But you guys are very smart. You've lasted this whole semester. Lab flow has not been easy. Believe me, when you guys don't like labs, now you know that each lab is taking me about 20 tries to get all the answers that I can get. So I'm being punished for it. It's all right. Makes me understand what you guys have to go through. You have to complete the pre-lab. I would suggest you make sure you understand these equations. The example problems I gave you guys, and some of the slides. I've given you some hints on other things in the slide, this lecture. You need 2 graphs. Pure and unknown with solvent. You need the equations. You're actually not going to upload the graphs. So how you do them it's up to you. But you need the equations for them. You're not getting out of that. Everything that we're solving for part B is from your calculated information from your graphs, not just by looking at it. Part A, do your best. Try to plug in what you can. See if you get anything right. If you get any of those in the correct format, I will give extra credit points. So let's say I'm giving you full credit for part A. Doesn't matter. But if you get any of that stuff right, so say, like for instance, I got, I think 4 things right on here. 1, 2, 3, 4, 5. I got 5 points. So I will give, for anything that's answered correctly on here, especially the ones that I can't get, I'll give extra credit points. Each one will be worth 1 point. So let's say I'm getting credit for this whole section. I have 5 points. I will add those 5 points to a lab. Okay? So that should give you guys some incentive to try to answer these correctly. because I know what slope is. Y equals mx plus b. I tried to do, I don't know. I don't know. And LabFlow was not very helpful. Part B needs to be completed, so you need to do that as best as you can. I will be grading Part B. They have allowed 2 attempts for this lab. So let's say you submit it once and some of the things are wrong. It's going to allow you to do it a second time. So you can, nothing changes on it. It'll show you what's wrong. You just got to type in over that and with what you think is the correct answer, but you only have 2 attempts and that's it. If you need help on the lab, Tuesdays and Thursday evenings I'm available. I know this lab might be a little overwhelming, so that's why I want to help. If you don't know how to graph, I use Google Docs. I can show you really quickly how to do that, but there's tons of YouTube lectures and so forth. You really should learn how to graph, because if you're going continuing in chemistry or a lot of other, difficult courses that have to do with science, you're going to have to learn how to graph. That's just something that you're not going to get away from. So if you need help, please contact me. We can make a quick appointment to show you, or if I can help you with this. Okay? And if not, this concludes our last lab.